Well, spring break got to be longer than we expected, so I figured I would go ahead and put together a video for the last class we had before spring break. So here's class 13 in abbreviated form, hopefully. We're going to cover the basics of rigid body kinematics. Relative velocity is the subheading on this. What we're really talking about is something that's in pure rotation. The bottom line up front from our equation sheets, we see that when we have pure rotation, we take, and we want to find the velocity, we have the cross product of the angular velocity times the position vector, where the angular velocity can be written out as either omega or theta dot. They mean the same thing. And in one plane, that's about the k-axis, or the axis that's coming out of the page. We also can have we could also have acceleration, which we will cover in more depth in a later class, but we will see that it is more complicated, just like it was with particle kinematics. When it came to translation, well, we have some extra terms that we have to worry about. Now, similar to particle kinematics and rigid body kinematics, we have angular velocity, just like we had translational velocity. So angular velocity is the time rate change of the angular position. And the angular acceleration, which we call alpha, is going to be the time rate change of that angular velocity. It can also be thought of as the second integral of the change in angle with respect to time. Or we have a third way to write the angular acceleration, which is the angular velocity times the time rate, not the time rate change, but the position rate change of the angular velocity, right? So this is very analogous to acceleration being dv dt, or d, and we could say x as just a generic position variable, and we also had v dv dx, right? So you could see we already know some of those things. And similarly, right here for uniform motion in angular terms, in terms of angles, we could find, and by the way, this angle has to be expressed in radians, right? Not in degrees. So we always had to convert to radians. So we could find that a final angular position, when it's a constant angular velocity, is going to be the original angular position plus the angular velocity times time. When we have the special case of uniform or a constant angular acceleration, we find that the final angular velocity is equal to the initial angular velocity plus the constant angular acceleration times time. And just as we would expect, we would write out that v is equal to VO plus AT. But now we're just replacing the v with omega and the a with alpha. In a similar way, we could have the angular position if we know the original angular position, the initial angular velocity, the time, and then the constant angular acceleration. And then don't forget the wild card, right? This comes from this, right? By taking the integral of that type of acceleration, we're able to find the final angular velocity with the squared equals the initial angular velocity squared plus 2 times the angular acceleration times the change in angular position. Right, so that's like the equation sheets that we want to know, and that's the bottom line that we're trying to get from this class. We also want to introduce chapter 15 as part of this class, and that's where rigid body motion comes in. So, but that first part of the chapter is just pure rotation. But we want to introduce these the flying potatoes, and it's just making a joke that the book shows these when they're three-dimensional as potatoes, and then when it's just 2 dimensions, they show them as potato chips. And the really important thing, the bottom line, is that all rigid body motion can be expressed as a combination of translation and rotation. So I should have written that up here. Right there. Boom. Make that the thing, rigid body motion, the thing that you should jump to. The big idea and concept is that rigid body motion is a combination of translation and rotation. And for us, we like to use this in a diagram. And it's a 3-part diagram where we say that the motion here is equal to the translation plus the rotation. Let's see, let's snooze another 5 minutes on that WebEx meeting. And yes, so we will see this in more detail in class 14. This is class 13 today. But this is a really important thing. We also see in class 15, which is going to be the ICR, that there's a magical point. Let's see, move this guy right here. There's a magical point about which a rigid body will appear to be rotating at any particular instant, and that's the instantaneous center of rotation, an important concept. The first way to discuss this translation and rotation is to first talk about pure translation and try to define what that means. Well, for a rigid body, a good way to try to express its motion is to pick 2 points. These points can be arbitrary. Sometimes they have some type of meaning. They could be attached to something else. So sometimes if we have a series of rigid bodies and a linkage, we might attach them at their joints. But we also might just pick 2 really good points to try to represent the location. And by rigid, we mean that this position vector that we have between these 2 points, which is a relative position vector, it doesn't really clear right there. So we say that B is something that's, we're used A as a reference to try to locate B, but this position vector does not change in length. That's what makes it rigid. If it were to change in length, that would be like mechanics and materials, right, where we would have some type of strain going on. But no, this is a rigid body, so that relative position vector does not change. And if this thing is in motion, and remember, what do we remember about velocity? Velocity is always tangent to the path. That should be our knee-jerk reflex reaction when we hear the word velocity. Is always tangent to the path, right? So if that's true and we have something that's in pure translation, then both of these velocities need to be parallel with each other. And if that's the case, then it's in pure translation. And the paths are also parallel lines, and these velocities are tangent to that path. When we get to acceleration, we'll see that the accelerations are also parallel to each other, but if there's some curvature to the path, the accelerations are not tangent to the path. They will have a part of them that points towards the center of the curvature. And then that was the special case of pure translation. If we have a special case of pure rotation, which is really the topic du jour, we will have an axis about which this thing spins. And we will see that in order to get the velocity in that case, we're going to take the omega of the thing, and we're going as a vector and cross it against the relative position vector, or the position vector to a particular point. If we want to get the velocity of that point, we find that velocity is equal to omega cross product with r. In pure two-dimensional pure rotation, this is going to be look like this right here, where this is the position vector, and we're going to find that velocity with that cross product. When we know in 2 dimensions that omega is just going to be the omega scalar value times k right there, and then that position, and we'll see that that velocity is going to end up actually being perpendicular to the position vector. And we could see that when we take this angular velocity times that, that's going to create that velocity. So a lot of times we could just think of the scalar is going to be this right here. And also we could also write that it's going to be theta dot r, right? So either one of those. And one way of thinking of this, right, that will help in trying to cement this idea right here. Here is a good one to memorize right there, is that if we were going to take a line and it was going to have some motion to it, and at a different angle time right here, we would have moved through an arc length, right? I'll say like delta s, and this is delta theta, right? So if we had, and this is r, if we wanted to find delta s, it would be equal to r delta theta, right? That's just, and of course theta is in radians right there. But now if we just take over time, and we could see that v is equal to r theta dot, which we also, of course, express as r omega, right? And then this was supposed to be funny, right? Because it's a record player, and it looks like this, and if you pick a point onto the record player and look at it, but your grandparents will know what a record player is. Of course you know what a record player is. It's just a joke. Ha. And I've already kind of gone over this, the corollaries, but here's a good summary of them and how they look alike and how you already know this. So when you have some type of angular setup to something, and you want to try to think of the kinematics, just think of all the corollaries to them. Some ideas that are important to organizing or to taking a look at rigid bodies with velocity is know that for something that's connected to each other, they have the same velocity. It's kind of obvious, but maybe not. It's something we need to say. Also, if the wheel is not slipping, a point in contact between there, the velocity here is going to be equal to 0 at point C. Because the velocity on the ground is equal to 0 right there, just because of this idea of an attached point. If they're attached to each other, at least at that instant in motion, they can't have the different velocities. They have to have the same velocity. We'll see later some other aspects of this that's going to be quite interesting, right? So this has like a velocity right here. We can actually get this omega from that because this is a point of reference. In this instant, we could pretend this is in pure rotation about this point, and we could find what this velocity is just going to be equal to that omega times that rg with respect to c. And we'll find in a similar way, we've been using red a lot right here, we could also find, and this is the idea of the ICR that we're going to have in a couple classes. Actually, it's going to be pointing more perpendicular to that thing, that we're going to find that velocity. And one thing that another aspect that's good to recall is that we have, if for an angular velocity, it's not actually about any particular point. Everywhere on a rigid body has the same angular velocity. So we don't need to do it. A lot of times we will say it's rotating about something right here, but that doesn't mean that the angular velocity is different from one position to another. The velocities are, by definition, have to be for the rigid body, but the angular velocities aren't different. This was walking through sample problem 15.1. This is in the book, so we don't necessarily have to go through these. You can go walk through this yourself. I thought at one time that was a good idea. All right, so for Hibbeler, here is an example where we have a couple points. This is like a pulley problem here, and it's a constant, right? So there's a constant angular acceleration right here, and we want to determine the magnitude and acceleration of point B that's on it. And I didn't give myself a lot of room, but we'll just write a little smaller. So what we want to do here is, after it's moved 2 revolutions, right? So when A rotates 2 revolutions, right? So they're not calling this a particular, they're saying this is going to rotate around twice and whatever. It's going to rotate around twice. I drew it the wrong direction. It's going to rotate twice, and we want to find out what the magnitude of the acceleration of B is going to be on pulley at that time. So we find out, let's go ahead and figure out what the angular velocity of a point on A is going to be, or an A point, but the whole thing. So the angular velocity, because we have positions, because the position has changed, the delta theta A is equal to 2 revolutions, which is 2 pi, by the way. So we find using the constant acceleration angular positions, we have 2 alpha A, which is constant, times the, I'll just put this as delta theta A. All right, so we have omega A squared is equal to this initial velocity. Oh, wait, at the instant shown, VA. Okay, so they're actually, oh no, that should be omega A, shouldn't it? We need to fix that. Yes. Okay. So that was a mistake. I don't know if I made the mistake. No, I didn't make the mistake. That was Hibbeler's mistake. So there's 5 radians per second squared, and it's moving in the same direction. They're showing the original arrow right here shows that it's counterclockwise, so that it is accelerating, right? The angular acceleration could be in the opposite direction as the angular velocity, because it could be decelerating. So there's 2 times our 6 times our 2 pi. And we get all those together, take the square root of it, and we get 13.258. That's a lot of sig figs. Radians per second. Now, if you want to get the angular velocity of this whole assembly right here, we could take a particular point on here, right there, right? So that's going to be V of that point, and that's going to be RA omega A, right? And then you have another point right here, and then they have to be the same velocity right here. I'm picking the points that are just tangent to that pulley. Cable, and so that's going to be V, and we can call that, we'll call it C. It's a point that's on C, and it's going to be RC omega c. And by the way, we also know by looking at this that omega c is going to be equal to omega b. So we could set those velocities that equal to each other, and we're able to say omega c RC is equal to omega a RA. So omega c times, and we can use millimeters. We don't have to change it into meters. We could, but that's going to be 40 because they're just going to cancel out. And 13.2588. Silly to write all those out. 50, and we get omega c is equal to 16.5735. Wow, they really went crazy with those sig figs here. And let's change to another color for acceleration. We can also say that the tangential acceleration right here, okay, so is going to be a at I guess right there, the acceleration here is going to be alpha a RA, and then right here in the tangential direction, and maybe we should put the tangential direction, AC tangential direction is going to be RC alpha C. So I switch those around. Alpha C RC is alpha A RA. Therefore, sticking these guys in here in the same way, we had 6 times our 50, and we get the alpha C is going to be 7.50 radians per second squared. And let's see. Now we could say that the tangential acceleration of B is going to be alpha, and we'll call it C, but now it's going to be RB, right? So that's going to be anywhere on here, somewhere is going to be this tangential acceleration. But there's also going to be, I'll write over here, a normal acceleration of B. And that's going to be AB normal. And that is the centrifugal part. And we like to write it, and when we're doing with these angular ones, we like to write that as, let's see, I guess I'll go with C. But now it's RB is the one. Okay, noteworthy is that can also be done if we found the velocity of a point on B and we squared it and divided by RB, that we would end up getting the same thing as this right here. This might be more familiar to us from particle kinematics, but it's just as equally as valid to write it either way. So we take our 7.5 and we multiply it by our, I guess we should use meters. Sure. So it's 60 millimeters, so it's 0.06 meters is the radius of the thing. And we end up with 0.450 meters per second squared. And down here we have our 16.574, I could have squared, and 0.06, and this is a larger number, much larger, 16.48 meters per second squared. So when we go for the magnitude, which I'll write up here, the magnitude of some point on B is going to be the square root of those two things squared, and what we end up finding, because one is so much larger than the other, it's 16.487 meters per second squared, or we could just say that the magnitude is 16.5 meters per second squared. All right, so that was another example. That was an example, but just to keep you in the loop, and I know some of you will be doing the homework again, or doing the homework soon. So this was a refresher. So I'm going to end the show now and go do my conference call. So hope this helped.